So in this lecture, I will talk you through how we define a differential equation mathematically, as well as some attributes that we can derive from those equations in terms of classification. So the first thing is that we will be looking at some function of x, where f is a function of a single independent variable x. Then the form of a differential equation is taken on as such, right? We have some function f, which is a function of the dependent variable, and some of the derivatives of the dependent variable. Okay, and that's what I've outlined within the section at the bottom. So I've talked you through the fact that a differential equation contains the dependent variable, and you can see that there. It contains the dependent variable y, and it contains some of the derivatives of that dependent variable, right? Some of its derivatives, which I've highlighted to you there. Any equation that follows or that structure is called a differential equation. If we talk about notation, there are various ways in which we can write out the derivative of a function. So the first notation that you would have come across is what we call Leibniz notation, right? And here, if I have a dependent variable y, all of its subsequent derivatives are written with the derivative operator d by dx. So dy by dx is the rate of change of the first derivative, the second derivative, and the nth derivative. And as I've noted, the advantage of using this notation is that it is clear to you what the dependent variable is and what the independent variable is using Leibniz notation. The second notation that you might have come across is the prime notation. So here the dependent variable y and its subsequent derivatives are illustrated as such. The first derivative, the second derivative, the third derivative. From the fourth derivative onwards, we assign the value of the derivative as brackets and the fourth derivative, brackets the fifth derivative, and the nth derivative. The last notation that you'll come across is what is known as Newton's dot notation. In this notation, we're looking at the independent variable being time. So here specifically, we're looking at, or exclusively, we're looking at differentiation with respect to time. And here x is the dependent variable and time is our independent variable. And this is the notation for any dependent variable. The way in which we describe subsequent derivatives of that dependent variable is by assigning dots to describe the first, the second derivative, etc. Now let's talk about the ways in which we can classify a differential equation. The first way in which we can classify a differential equation is by its order. So what I've defined order as is the order is defined as the highest derivative of a differential equation. So let us look at a few examples of this. Let's say we have a differential equation d squared y by dx squared plus dy by dx minus 4y equal to e to the x. Okay, so if I want to classify this differential equation by order, I need to look at which is the highest derivative that occurs in this equation. Obviously, it's a differential equation because I have some unknown function y with a relation between some of its derivatives. So I have the first derivative here, I have the second derivative here. So the occurrence of the second derivative here makes this equation a second order differential equation. Okay, let's look at another example. Say I have y primed plus 4y double primed plus 6y, the fourth derivative, equal to sine x. Again, here this is a differential equation. I have some function of some dependent variable y and a relation between its associated derivatives. I have the first derivative, I have the second derivative, and I have the fourth derivative. So in terms of the highest derivative in this equation is the fourth derivative. That's clear. The highest derivative here is the fourth derivative, and so we can describe this differential equation as a fourth order differential equation. So order is a fairly simple way of classifying a differential equation, and to summarize, the way in which we describe or classify a differential equation by its order is that it's named after the highest derivative that occurs within the differential equation. So for the purposes of this course, we will begin with a first order differential equation. We will start with first order differential equations. What that means is that the highest derivative occurring in that differential equation is the first derivative. Okay, it only contains derivatives of the first order, and these typically arise in population modeling and in free-fall physics problems. So these types of first order differential equations have some relational context. As the order increases, so as we go from first order to second order and to higher order differential equations, it becomes very difficult for us to use some analytical method to find a solution to those differential equations. And in those cases, we will try and find approximate numerical solutions using packages like MATLAB or other numerical techniques when those analytical methods fail us or are not possible to be implemented. The second way in which we can classify a differential equation is by its linearity. So it's very important that you understand this definition of linearity. So let's go through it and let's unpack it. It says that an nth order ordinary differential equation, first of all, an ordinary differential equation is a differential equation that only contains full derivatives. It's a differential equation that only contains full derivatives. They do not contain partial derivatives. Okay, and such equations that only contain a full derivative is called an ordinary differential equation. So an nth order differential equation, what does order mean? We're saying a differential equation that has the highest derivative is the nth derivative, right? So an nth order ordinary differential equation is linear, right? The differential equation is linear if, and two things need to hold for it to be linear. The first thing is that the dependent variable and all of its derivatives are of the first degree. And what I mean by degree is that the power of each term involving the dependent variable is 1. Okay, so let's unpack that a little bit. So first of all, what it says is that we need to be looking at the dependent variable. We need to look at the dependent variable, right? The dependent variable and all of its derivatives, all of the derivatives of the dependent variable. So for example, if my dependent variable is y, and I have some of the derivatives of y, what the first point is saying is that the dependent variable itself and all of the derivatives have a power of 1 only, right? The power of each term involving the dependent variable is 1. So we're saying here that the power here should be 1, the power of the derivative there should be 1, the power of the derivative there should be 1, the power of the derivative there should be 1. Any term involving the dependent variable itself or any term involving the derivatives of the independent variable, if they occur, the power of those terms should be 1. Good. The second thing that needs to take place, and the second thing we need to be aware of, is that the coefficients of any of those terms, the coefficients of any of these terms involving the dependent variable or involving any of its derivatives, those terms, or those coefficients rather, can either be constants, they can either be a constant. The first thing they can be is a constant. They can either be a constant or they should be functions of the independent variable only. Okay, so let's unpack what that is saying. What that is saying is that if we have any terms preceding the dependent variable or any terms preceding its derivatives, those terms should either be a constant, or they should be functions of the independent variable. And that's the only two cases that hold here. If those two do not occur in this way, then that differential equation is no longer linear. Okay, so let us look at a few examples to unpack linearity. So let us look at the first example. It says y double primed minus 2y plus y is equal to 0. Let's already classify this in terms of order. We have the second derivative there, so this is a second order differential equation. In terms of linearity, the first thing that we need to look at is the dependent variable, which in this case is y, and any of its derivatives need to occur to the first degree, i.e. their power should be 1. It's clear here that each of these terms involving the dependent variable or its derivatives, the power is 1. So the first thing is correct, right? The first thing, which is that the dependent variable and all of its derivatives are of the first degree, the first check is correct. The second check says, look at the coefficients of all those terms involving the dependent variable. The coefficient of this term here is 1. The coefficient of this term here is 2. The coefficient of this term here is also 1. So all of those are constants. So we're told that it can either be constants or functions of the independent variable. So the second aspect we've checked. And so based on these two checks, we can now conclude that this equation is in fact linear. Okay, let's look at the next equation. The next equation says, I've got the fourth derivative with respect to time minus sine t equal to y, and here y is a function of t. First of all, let's describe that differential equation in terms of its order. The highest occurring derivative is the fourth derivative, and so this is a fourth order ODE. Right. In terms of linearity, the first thing is look at all terms involving the dependent variable and any of its derivatives. The degree of those terms should be 1. The degree of both of these are 1, and so the first check is being satisfied. Both of those terms have a degree of 1. The next thing is that we need to check the coefficients of any terms involving the dependent variable or its derivatives. Both of those have a coefficient of 1, and so the second check we have made. Now there's an interesting term here, which is sine t. This term here does not make this equation nonlinear. This term here does not make the equation nonlinear. First of all, sine t is a nonlinear function, but it's nonlinear in the independent variable only, right? It's nonlinear in the independent variable only, and so this term here does not involve the dependent variable. This term here does not involve the dependent variable. So in actual fact, because both of those checks took place, this equation is linear, regardless of the fact that this term is nonlinear in the independent variable. I want you to understand that idea fully. Okay, let's look at the last differential equation, which is written in Newton's dot notation. So we have the second derivative minus 2 of the first derivative equal to t squared plus 3x. It's clear here that x is the dependent variable, which is a function of time because we have Newton's dot notation, which is exclusively with respect to time. Okay. First, let's categorize this or classify this by its order. The highest occurring derivative is the second derivative, and so this is second order. In terms of linearity, the first check says, look at any terms involving the dependent variable or its derivatives, and check that the degree is 1. The degree of all of those terms is 1, and so the first check is done. The second thing says, look at the coefficients of the terms involving the dependent variable and any of its derivatives. Those coefficients have to either be constants, that's a constant, that's a constant, and that's a constant. And so the second check is done. We can already conclude that this differential equation is linear. The fact that we have a term involving the independent variable t that occurs in a nonlinear fashion does not make this equation nonlinear. The fact that we have t squared here and t squared is nonlinear in the independent variable, that is irrelevant for our check of linearity here, and so this equation is in fact still linear. Okay, so then the question is then, if a differential equation is nonlinear, how do we know that it's nonlinear? It's easy. It's nonlinear if one of those two conditions are not met. If the above conditions do not hold, the ones that I talked you through, the equation is nonlinear. That means that they're either nonlinear functions of the dependent variable, or some of its derivatives in the differential equation occur nonlinearly. It does not matter, as we've seen in the previous slide, if the independent variable occurs nonlinearly on its own, it does not matter. So let's look at a few examples and unpack them. The first example is with regards to the first equation is with regards to a second order differential equation, right? The highest derivative is the second derivative, so it's a second order ODE. And let's unpack the two checks. The first check is look at any term involving the dependent variable or its derivatives. This term involves the dependent variable. The degree is 1, and so that's okay. The problem arises in the next term, because we now have something that is a function that is a transcendental function. We have sine y. So we have sine of the dependent variable. This is nonlinear in the dependent variable y. This is nonlinear in the dependent variable y, and as such, this differential equation is nonlinear. Why? Because they are nonlinear functions of the dependent variable that occurred. Okay. Let's look at the last example. We can already classify this by order. The fourth derivative is the highest occurring derivative, and so this equation is a fourth order derivative. Let's now unpack the idea of linearity. The first thing is check each term involving the dependent variable and any of its derivatives and check that the degree is 1. For here, the fourth derivative of the degree is 1. However, this term involving the dependent variable x here, clearly x is the dependent variable here, t is the independent variable. This term here involving the dependent variable x occurs non-linearly. The degree there is not 1. The degree there is not 1. The degree of this term is not 1. And so that makes this equation non-linear. As an exercise, I leave you with these 3 questions, and I want you to check or classify. First, check whether these 3 are differential equations to begin with. And secondly, I want you to classify each of them in terms of their order and in terms of their linearity based on what we have just done.